Hello students, this is your Professor Dr. Mink. Welcome to another mind-expanding lecture for Computer Organization CSE 240. The topic of the day is the von Neumann model. John von Neumann was a mathematician who wrote a paper, a concept paper, in 1945. And it's scary how accurately he described modern computers. Let's discuss this further. The first device identified or characterized as a computer was the ENIAC. And that was developed in 1943. So you'll see a lot of the events in the early to mid 40s helped to solidify the concept of a computer. The ENIAC was an analog device. There were dials and switches. There were no semiconductors. And it was the beginning of what called the EDVAC era, which EDVAC stands for Electronic Discrete Variable Automatic Computer. And there it is, the word computer. And it described, simulated a device that included a program stored in some memory. And the first draft of a report on EDVAC, this conceptual framework, was written in 1945 by John von Neumann. And in his paper, he proposed a von Neumann machine or von Neumann model consisting of a memory that contained instructions and data, a processing unit that performed arithmetic and logical operations, and a control unit that interpreted these instructions. I've found a really, really good MIT open source video lecture on the von Neumann model, and I placed it in the timeline of Canvas for this module, this course module. I'd like you to pause and go watch that. It's very short. I think it's 8 or 10 minutes, and it's really, really good. In this diagram, we take the three components of the von Neumann machine or von Neumann model: memory, processing unit, control unit, and we include the contemporary names of components within those categories. And within the processing unit, the processor, we have the arithmetic logic unit, and then we have temporary volatile memory. And you're going to see that involves registers. And the registers are the exact size of the architecture. And so what does that mean? In the case of the LC3, the simulator we're going to be using, that means that everything within the processing unit, the arithmetic logic unit, and all the temporary storage used to assist with processing data is 16 bits wide. The computer that I'm using now to digitize this lecture is a 64-bit architecture. And we're going to get into that as you move from 16 to 32 to 64, you basically gain range and precision and capacity, instruction capacity. So outside of the processing unit, we have the program counter, which I'm sorry, the control unit, which has the program counter and the instruction register. The program counter points, you're going to see this firsthand when we start programming. The program counter holds the address of the next instruction to be moved into the instruction register. That's the IR. And we also have access to memory. And we have the memory address register, which holds the address of a memory location. And the memory data register actually holds the contents of the address of the data that's in the address pointed to by the memory address register. And obviously we have external input and output added to the process so we can get data in and data out of the program, out of the device running the program. In chapter 3, we explored a 2 to the second times 3 memory constructed of gates and latches. You remember that. Hopefully you remember that. A more realistic memory would be 8 bits times 2 to the 28th. That's 2 to the 28th distinct memory locations, each 8 bits wide. That would be an 8-bit instruction set architecture. Still quite obsolete. Well, I shouldn't say that. Many of the devices that we use today have microprocessors embedded in them. I'm looking at my smartwatch right now. I doubt very much that has, I don't know for sure that has anything beyond an 8-bit processor, because it can go almost a week on a rechargeable battery charge, and the battery's not that large. So it would be overkill putting a 32-bit or 64-bit processor in a device that has a very limited instruction set. And it would be inefficient from a energy standpoint. It would just be too energy inefficient, and the thing would have to be 5 times the size it is now, which would make it kind of awkward to wear on your wrist. So anyway, so we say, going back to the 2 to the 28 memory locations by 8 bits wide, we say that the memory has an address space of 2 to the 28th, whatever that number is, uniquely identifiable locations, and an addressability of 8 bits. That's 256 megabytes. To read the contents of a memory location, we first place the address of that memory location into the memory address register and then interrogate the computer's memory. Some basic operations to consider: load and store. These are our first micro instructions we're going to use. Load reads a value from memory location into the processor, and it will read it from a memory location to a general purpose register. First time you're hearing that, it's not the last time. We're going to talk about general purpose registers ad nauseum. Store writes a value from the processor to a memory location. So how does the processing unit get data to and from memory? Well, we have 2 registers, the memory address register, and in the case of the LC3, guess how wide it is? You in the 3rd row. Correct. 16 bits. Yes, because that's the size of the architecture. And so the memory address register and the memory data register, both of which have to be 16 bits wide. The memory, by the way, the memory address register in the computer I'm using is how wide? You got it. 3rd row, 4th seat in. Yes, that's correct. Did you hear that, everybody? It's 64 bits. It has to be. That's the architecture size. Sorry. So to load a location A, we write the address A in the memory address register. We send a read signal to the memory, and then we read the data from the memory data register to store a value X to location A. And A would be a hexadecimal memory address, but we'll get to that. To store a value X to location A, we write the data X to the memory data register first, and then we write the address A into the memory address register and send a write signal to the memory. Here is figure 4.2 on page 99 of your textbook. Memory consisting of 8 locations with addresses on the left. Each location stores a byte, which is 8 bits. Next up, the processing unit, also called the CPU. It has various functional units depending upon its purpose. A general purpose CPU for a computer has many functional units, some special purpose, multiply, square root, etc. The simulator that we are going to learn performs add, and not, so it is logically complete. Processing unit also has some temporary storage locations that are called registers. They store operands and results of functions that are about to be performed. The LC3, the simulator, has 8 registers, R0 through R7. Each of those registers is 16 bits wide. If it has 8 registers, how do you think each register is addressed? What is the address of the first register and the last register? And how is that designated? Well, we're in a binary system, so we've got R0 through R7. We got 3 bits, 000 through 111. The word size, which is the number of bits normally processed by the arithmetic logic unit in one instruction, is also the width of the register, 16 bits. The terms input and output should be commonplace for you. Let's talk about devices. Okay, the input devices are used to get data into the computer, and output devices are used to display output. There's obviously an explosion of input devices. Biometric authentication, especially in this era of cybersecurity, has become fairly commonplace. Just got a new phone, has a fingerprint scanner on it. Actually, my other phone had fingerprint scanning, and that's about 4 years old. So there's the universe of input devices is expanding rapidly. Output devices, I wouldn't say, are expanding as significantly. Facial recognition, retinal scanners, all kinds of things. So each device has its own interface, which is usually a set of registers, like the memory address register and memory data register. In the case of the LC3, being a simulator, it supports keyboard input and monitor output, both of which are ASCII devices, which we'll get to when we start programming. Each device has 2 registers, one for status and one for data. The keyboard has the keyboard data register and the keyboard status register, and the monitor has the display data register and the display status register. One is used to indicate input or output is ready, and the other is to hold the actual input or output. Some devices provide both input and output, and the program that controls access to those types of devices is usually called a driver. And it's a program that works with the specific device and the operating system. Whenever we solicit input or send output to a peripheral device, we need an operating system. The operating system of a computer manages the hardware. So there is some handshaking. And for that reason alone, we start out the programming component of this class with our data hardwired into memory. We're actually not soliciting data until later in the class because that adds another level of complexity. It's not very complex, but it's easier to start off with data that we just place in memory as opposed to having to deal with the control unit. I'm sorry, the status register, the data register, etc. The control unit is the traffic cop, if you will. It orchestrates execution of the program. And the control unit has two key components. The instruction register, which contains the current instruction. And what does an instruction look like? Well, every instruction held in the instruction register on the computer that I'm using, which is a 64-bit architecture, every instruction is 64-bit wide. In the LC3, the simulator we're going to use, every instruction is 16 bits wide. So the instruction register holds the current instruction. The program counter contains the address of the next instruction to be executed. So the control unit reads an instruction from memory. The instruction's address is in the program counter, 16 bits wide. It interprets the instruction and then generates signals that tell other components what to do. An instruction may take more than one machine cycle to complete. I cannot think of an instruction that takes just one machine cycle. That would be, yeah, I cannot think, I don't believe there is any formal instruction, coded instruction that takes just one machine cycle. They all take, there's a lot of moving parts. And when we get into the information processing cycle, you'll see why that's the case. A lot of people think one clock cycle, one instruction, that would be ideal, it would be utopian, but that doesn't work that way. As I just mentioned, executing a single instruction, and in the case of the LC3, it's a 16-bit instruction, and we'll get to dissection of an instruction. It takes multiple machine cycles. Remember, one cycle, one clock cycle, is the smallest increment of change, state change. Here are all the possible steps in the instruction processing cycle. There are some instructions that don't move data and don't need to evaluate addresses, and then therefore don't have to execute that part of the instruction processing cycle. And we're going to dissect each one of these in great detail. So first thing that happens is they fetch the instruction from memory, decode the instruction, evaluate addresses if there are addresses in the instruction, if it's a data movement instruction, or if it's a load command or a store command. Fetch operands from memory, execute the operation, and store the result. So those 6 steps are the maximum number of steps it takes to process a single instruction. Some instructions skip certain steps, and we'll get to that in great detail coming up. The instruction is from a programming standpoint, it is the smallest or fundamental unit of work. And it specifies two things. The opcode, which is the operation to be performed, and we're going to look at the instruction set next. The opcode for the LC3, which is a 16-bit instruction set architecture, uses a 4-bit opcode. So we could have up to 16 instructions, 0, 0, 0, 0 to 1, 1, 1, 1. So it includes the opcode, which is 4 of the 16 bits, and then the operands, the data locations, the data and/or locations to be used for the operation. An instruction is a sequence of bits, zeros and ones, just like data. There's very little discerning difference between an instruction and data, and we'll get to that in a second. In the case of Intel type processors, instructions have a fixed length, and all of the instructions in the LC3, which is a 16-bit instruction set architecture, are 16 bits wide. The control unit interprets the instructions and then generates a sequence of control signals necessary to carry out whatever operation the instruction calls for. An operation is never partially executed. It's executed completely or not at all. So a computer's instructions and their format is known as the instruction set architecture, the ISA. I've mentioned that multiple times up to this point in the class, but it is a key term that will be used over and over and over again. It really is the fundamental topic that we're going to be covering for the rest of this class. This slide is from Appendix A, and I've posted Appendix A in the timeline of Canvas. And it is kind of the user manual for the LC3. And it has a plethora of really important information. But the most important page in Appendix A is the opcode listing. This is, my friends, the instruction set. So on the left, we have the mnemonic for the instruction. So example, add. Obviously, that adds 2 operands and stores the sum. You'll notice that it has a syntax, a 16-bit syntax on the right of the mnemonic. So let me just go through add, and then I have a series of videos that I think come from the publisher on the different operations. So add, its opcode is bits 12, 13, 14, and 15, or 15:12. The opcode is 0001. The address of the destination register, remember we have 8 general purpose registers. The destination register is the register where the sum of the 2 operands is stored in the last step of the information processing cycle. That is coded in bits 9, 10, and 11. And you'll see DR stands for destination register. Source register number 1, the address of the 16-bit register, 000 through 111, that holds the 16-bit value that's going to be the first operation in this binary add, is stored in that address and stored in that register. And that register's address is encoded in bits 6, 7, and 8. Bit 5 is a switch. It's a toggle switch. 0 for register mode, which means operand number 2 is stored in a register. and that register is addressed in bits 0, 1, and 2. Or you'll see a second add command, or a second version of the add command, where bit 5 is 1. And that means that operand number 2 is, okay, hold on to your seat, is a 5-bit 2's complement sign extended value, sign extended to 16 bits, which means we are coding operand 2. So we're going to add the contents of source register 1 with a 5-bit sign extended to 16-bit 2's complement value. Now you'll start to appreciate why we spent that time on the numbering systems. So I strongly urge you to print this page from Appendix 1 or all of Appendix A, so you'll have this as a handy reference. We're going to use it for the rest of the class extensively. At this point in time, I'd like you to pause this video, go to the timeline section in Canvas, and watch the LC3 add instruction. I think it's add, and not, and branch, actually. And it is really important that you watch that video. I know what you're thinking, I'll just skim it or whatever. It would be a catastrophic mistake on your part to not watch that video, because you're going to be lost moving forward. I put it there. I would create the video myself, but I could not do a better job than the one I found. So please watch that, and then we'll talk more about the specific instructions. Okay, how'd you enjoy that video? Let me ask you some questions about it now. You in the fourth row, tell me about the video. Sorry, couldn't help myself. So here, let's skip back and let's dissect a 16-bit instruction. Okay, here we have the syntax up here. Shows us the different components and the bits. So we have a 4-bit opcode. In this case, it's 0001, which is add. Right? Add. So this is an add command. What are we adding? Well, we have here bits 9, 10, and 11 are the destination register. So this is going to store the result of this bitwise binary add in what's 110, 124. That's R6. That's register 6. 1, 2, 4. 2 plus 4, 6. Okay. So the first operand of this add, source register number 1, is here in these bits 6, 7, and 8. No 1s, 1, 2, no 4. So this is R2. So we're going to add the contents of R2. Bit 5 is 0. That means we're in register mode. So bit 4 and 3 are irrelevant. They're kind of ignored. And they're always going to be 0, 0. So the second operand is going to be stored in where? Well, what's 110? That's R6. So we're going to add the contents of R2 to the contents of R6 and store the result back in R6, thus overwriting what was in R6 previously. That's the dissection of an add command. Here we have another add command, and I deliberately chose all of the same bits as the previous add command except for one, bit 5. Bit 5 was a 0. So in this instruction, we have add. Our destination register is R6. Our source register number 1 is R2. But because bit 5 is 1, that means we're going to use all 5 of the remaining bits, bits 0 through 4, as a 5-bit immediate sign extended operand number 2. Well, how do we sign extend 0, 1, 1, 0, 0? Bit 4 is the sign bit, the most significant bit. How do we sign extend that? There you go. We just take the sign bit 4, we sign extend it because this can't be fed to the processor as a 5-bit value. So in one step in the instruction processing cycle, as we're fetching the operands, the immediate operand, the sign extended 5-bit sign extended value, 5-bit value gets sign extended to 16. What I would like to do now might be a little scary for some of you. I'm going to jump ahead and I'm going to write a small machine language program, but we're going to start off with the editor in assembly language. Now, this is going to be brand new, and if you're a little bit confused by this, that's okay, because we're going to walk through this in much more detail. But this, you should understand that every machine language, which is ground zero, that's what runs through the processor, every instruction set architecture for a specific machine language comes with a low-level programming language. Programming language means it has things like mnemonics, it has syntax. So this is the x86 assembly language. And the two statements I'm going to start off with, dot origin x3000, that means we're going to place this code at hex 3000 in the memory. That's the beginning of user space for the simulator. I know, lots of information. And the dot end just specifies the end of our program. So what I'm going to do is demonstrate the add and the and command. So think about this. These general purpose registers in the processor are being used by every possible program that runs on the computer. So when one program ends, another program, hey, let me in the processor, I'm next, right? The processor is handling a massive amount of tasks. And you'll hear the term multitasking. Fact of the matter is, the processor's only handling one task at a specific time, but it is so fast, and it can keep other processes paused, and we'll talk about interrupts and how that happens later in the class. So let's start off by clearing 3 registers that we want to use. Let's say we want to use register 0, 1, and 2. Well, how do you start with a known value? Because there was something in there from the previous program. Well, if you AND anything with 0, you get 0. So let's start with, let's AND R0, comma, R0, comma, pound 0. Okay, that is the AND command, and you had to have watched that video. I begged you to watch it, right? So the the destination register is R0. We're going to store the result of ANDing whatever's in R0, and the pound 0, pound instead of R, indicates immediate mode. So we're going to have a 5-bit 2's complement sign extended 0, 0, 0, 0, 0. So we're going to clear R0. Let's clear R1. And let's clear R2. So now they'll all be zeros. And by the way, this, anything after the semicolon is a comment. So I could do this. Whoops, sorry, I had caps lock on. So then let's use the add command. Let's add to R1 the contents of R1, which we now know is 0, and a pound 3. Just add 3 to R1 and store it back into R1, and then we'll add R2, pound 1, and then we will add R1, R2, I'm sorry, we're going to add R1 and R2 and store it in R0. And that's our program. You need to save it. First time you'll hit Save As, and you need to give it an ASM extension. I've called mine add.asm. So I'm just going to hit Save, but it has to have the ASM. And then this editor, which I've given you, the LC3 editor, it's in the first module of this class. The editor and the simulator. So I'm just going to assemble this. Get 0 passes, and then if I go into where I store my LC3 files, I just put it in Documents in a folder, add.binary, and I'm going to open this. Notepad. So let's go back. Whoops. There, my friends, is the the machine language. So this is our address. That's hex 3000. See it? 4 bits of binary for 1 bit of hex. There's 30000. Okay, what is this? And R0, bit 5 is 1, so that is a sign extended 0. My friends, you cannot rush through this part of the lecture. And if you're going to understand this, you probably want to watch this, rewind it 2-3 times. What is this? And R1, bit 5 is high, so that's a sign extended value. And this is the same. This is and R2, right? With 0. This is an add destination register R1, source register number 1, register 1. There it is. And there's our sign extended 5-bit 2's complement sign extended 3. 1 in the 0 command. 1 plus 2 is 3. Here's the same command, except we're adding R2, R2, 1. And here we're adding source register, register 0, the contents of register 1, bit 5, 0, 1, 2, 3, 4, 5. Bit 5 is a 0. So that is a register address. It is not a 2's complement value. I probably shouldn't do what I'm going to do next, but I'm going to, just so you can see what the simulator looks like. And we're going to do this in significant detail. There's my ad that I just created. There it is. We're running in the simulator. This is the console for the simulator over here. You'll see a second window open. Don't worry about that until we get to I/O. Whoops. So here's all my registers and their contents, the program counter and the instruction register. We're way ahead of ourselves right now, but what I can do is I can step into this program. These are not going to do anything because R0, R1, and R2, since I just started the machine, are already 0. Now we're going to add a 3. There's our 3 to R1. Add a 1 to R2. Now the final command right here. Add R1 plus R2 and store it in R3. I'm sorry. Add R1, add R2, store it in R0. Sorry. Talk about confusing. So, I mean, here's the part I want you to focus on. We're learning the micro commands, the machine language commands. We have the assembler, which we're going to learn at the same time. Remember, there's a one-to-one relationship between and the opcode. So that's a lot at once, and I'm sorry, not sorry, but we're going to cover this again and again and again in significant detail. But I just wanted to show you your first machine language program, albeit very simple. Now I'm going to ask you to pause this video, and right below it in Canvas is another, it's an external video. I found these and they're really well done, and I don't think I could do a better job. So I'd like you to watch the LC3 load instructions video. And it covers basic data movement commands, loading, and storing. And then we'll come back and talk about them a little bit. As you've just seen in that video that I know all of you watched, the load commands are used to read data from memory. You're reading data from memory into a general purpose register. Now please note, each one of these commands is going to be covered in very significant detail, and I'm going to have demos and we'll work together. And if you're having any questions about these, I can light up a GoToMeeting session with 1, 2, 3, 4 of you, a couple of you at a convenient time, and we can go over them. So I don't want anybody to panic because we kind of go hard and fast into this topic. So this command, LDR, which stands for load register, takes a full 16-bit memory address stored in a base register, and in this case it looks like R3, and it allows you to add an offset from that value, from that number, that address. And the offset is a 5-bit 2's complement sign extended value. To be honest with you, in most cases you're not going to use the offset, you're going to load a hexadecimal number, 16-bit hexadecimal number, or actually it's a 4-bit hexadecimal number to be stored as a 16-bit binary number into a register, and you're going to use that as the target address to load a value into the destination register. So LDR, its opcode is 0110. That's bit 12 through 15. That's the case with all opcodes. The destination register is bits 9, 10, and 11, and that's the location that the value loaded from memory will be stored in, the register location. And then you've got your base register, which holds the target address, and then you can have a 5-bit 2's complement sign extended offset from that register. Next topic, which is a very important topic, is the instruction processing cycle. And I'm going to walk you through each of the steps in the instruction processing cycle. And this is what happens when an instruction is processed. So the first step, fetch, it loads the next instruction, and the address of the next instruction is stored in the program counter. So it looks at the program counter and it moves that instruction into the instruction register. One of the first things that happens is that increments the program counter so that it points to the next instruction in the sequence. Excuse me. This is going to be a point of frustration for some of you, because before we even decode the instruction in the instruction register, the program counter is already pointing to the next instruction. So before we know what this instruction is, the program counter is pointing to the next instruction. And in some cases, the instruction in the instruction register, yes, it's getting a little convoluted. The instruction in the instruction register has a program counter offset. In other words, a value that gets added to the program counter to calculate a target address. But by the time we get to that point in the instruction processing cycle, the program counter has already been written over. It's +1. It no longer holds the address of the instruction in the instruction register. And this is a point of significant frustration for students, and many mistakes on our next exam or our next assessment are made in this arena, if you will. So we copy the contents of the program counter in the memory address register. We send a read signal to memory, and then we copy the contents of the memory data register, which is what's the memory address register is pointing to, into the instruction register. And then the increment the PC. So before we even decode the instruction, the program counter is +1. So then, after fetch, comes decode. Decode decodes the instruction. Identify the opcode is the first thing. And in the LC3, which is a 16-bit x86 instruction set architecture, it's always the first 4-bit of the instruction. So a 4 to 16-bit decoder asserts a control line corresponding to the desired opcode. Depending on the opcode, we may identify other operands from the remaining bits. So for example, LDR, the last 6 bits is an offset. For add, the last 3 bits is source operand number 2, etc. Hopefully you recall me mentioning earlier that not every instruction utilizes every one of the steps in the instruction processing cycle. Some instructions don't require memory access. They don't go out and access a memory address. So for those that do, we either add an offset to a base register, just like we saw in the LDR command. We add an offset to the program counter, which at this point in time is +1, or we add an offset to 0. Next step is to fetch the operands needed to perform whatever operation. Operand for a load command could be data from memory, or for an add command, read data from the register file, etc. Next step in the instruction processing cycle is execute. It performs the operation using the source operands, sends the operands to the arithmetic logic unit, and inserts the add signal for an add command. When it sends the operands to the arithmetic logic unit, if operand number 2 is a 5-bit 2's complement sign extended value embedded in the 16-bit instruction, that gets sign extended during this process. For loads and stores, nothing happens. Nothing happens during this. The final step, which we'll cover next, is how loads and stores terminate. Final step in the instruction processing cycle is store, or store results, and it will write the results to the destination register or memory. So the destination register for add and is placed in the destination register. The result of the memory load is placed in the destination register. For the store instructions, data is stored to a memory address. Remember, you're loading from memory to a general purpose register. You're storing from a general purpose register out to memory. Now, please remember, we are overviewing the major categories of instructions. And the next video I'm going to ask you to pause and watch is the jump instruction. In the fetch cycle, we increment the program counter by 1. But what if we don't want to always execute the instruction that follows? For example, if we want to deviate from a linear flow of control, instead of next instruction, next instruction, next instruction, we want a jump or a loop or a function call or whatever. So we have instructions that are called control instructions, jumps, branches, etc. So so far we learned the operate instructions, add, and not, and the data movement instructions such as load and store. A third type of instruction is the control instruction, whose purpose is to change the sequence of instruction execution from linear to nonlinear. So if we want to do that, we must change the program counter between the time it is incremented during the fetch phase of one instruction and the start of the fetch phase of the next. Control instructions perform that by loading the PC during the execute phase, which wipes out the incremented PC that was loaded during the fetch. Once again, I'm going to ask you to stop or pause and watch the LC3 control instructions video that I've placed right below this lecture in Canvas, and then come back. Okay, that was fast. Are you sure you watched the whole video? You didn't fast forward through any of it? Just kidding. Actually, I'm not kidding. So let's dissect the first control instruction, just to give you an example. And we're going to cover this in greater detail later in the class. But the jump instruction opcode 1100, really only has three other relevant bits. That's 6, 7, and 8. And they hold the address of a register of which holds an address out in memory that we want to load into the program counter. So first thing you need to do is get that address into the register. In this case, it's R3, 011. And we load an address, full 16-bit binary value, which corresponds to a 4-bit hexadecimal address. And this will, during the execute phase of this instruction, it will replace the program counter value that was incremented +1 during fetch. I know, it's getting a little convoluted here, but it's important that you understand all this. And it replaces it with a new address, and that will be the next instruction, whatever's at that address, that we jump to. So to summarize the two main topics we just covered. Instruction processing cycle. Instructions look just like data. They're all 16 bits wide. There are three basic kinds of instructions, or three categories of instructions that we're going to cover in the LC3. Computational or operation instructions, add, and, not, etc. Could also be thought of as arithmetic logic instructions. Data movement instructions, load and store, and then control instructions. The only one we've covered so far is jump, but BR and Z is branch, and we're going to get to that in great detail. And another really important topic is that you fully understand the 6 phases of the instruction processing cycle. Fetch, decode, evaluate, operands, execute, store. And that not all phases are needed for every instruction, and these phases may take variable number of machine cycles. So the thought that some students have coming into this is an instruction takes 1 clock cycle. That's not the case. Here we have a state diagram of the control unit. And this is a simplified state diagram, very simplified. But what we have is the value of the program counter during fetch is loaded into the memory address register. The program counter gets incremented +1. Then whatever the memory address register is pointing to, that whatever's there gets loaded into the memory data register, which ultimately gets loaded into the instruction register. Then we decode the opcode for that instruction, and we then assert a signal to an adder or one of the other circuits necessary to complete the command. There's a more complete state diagram in Appendix C. And as noted here, it'll be much more understandable after Chapter 5 when we start to actually drill down and dissect each of these machine language instructions. One of the things you'll find when we write our first program is the control unit will continue to repeat instruction processing, keep grabbing instructions as long as the clock is running. And so there is a way to stop the clock. Clock generator signal is needs to be 0. So when the control unit stops seeing the clock signal, it stops processing. Stopping the instruction cycle requires only clearing the run latch in this diagram. If the run latch is in the 1 state, i.e. Q is 1, the output of the computer's clock circuit is the same as the output of the clock generator. If the run latch is in the 0 state, the output of the clock circuit is 0. But once again, we're going to we're going to get into each of these concepts in much more detail. You need to understand the instruction processing cycle and each of the steps in the instruction processing cycle. That's really a key takeaway from this chapter. Oh, look, we're done. That's the last slide. So thanks for watching. Have a great day. Of course, you're probably going to have questions. Please don't hesitate to ping me in any way you feel. Email me through Canvas. Come to my office hours, which will be live, and ask questions. And I'll gladly help you. I like helping students understand these concepts. This is one of my favorite courses to teach because it's such an oddball course in the sequence. Thanks for watching. Have a great day.